Assalamualaikum warahmatullahi wabarakatuh. So, I am Muhammad Ifami Ramli and my group member Muhammad Izzuan bin Rahman, Nur Yasmin Afzan binti Azizan, and Nur Zulaika Azana binti Syahri Nizam will present you about subtopic 7.7 and 7.8. So, about 7.7 is about the TDS relation, and 7.8 is about entropy change of solid and liquid. Next. So, about the TDS relation. So, the differential form of the conservation of energy equation for a closed stationary system with fixed mass containing a simple compressible substance can be expressed for an internally reversible process. As you can see, the equation is delta Q internal reversible minus delta W internal reversible out equal to du. But delta Q internal reversible ni equal to T ds, and delta W internal reversible out equal to P d. This is not V. This is uh, dV. Okay. So from the equation just now, so we put we substitute into the first equation, so we can get the first TDS or Gibbs equation. This is the first equation, first Gibbs equation. TDS equal du plus P dV, and TDS equal du plus dV. This is the same. Plus P dV. The second TDS equation is obtained by eliminating du from equation 7.23 by using the definition of enthalpy. The equation 7.23 is at the yang kat atas ni, yang TDS equal du plus PdV tu. So the definition of enthalpy, H equal to U plus PV. So dH equal du plus P dV plus V dP. And then kita eliminate du tu. So kita dapat the second TDS equation or the second Gibbs equation is TDS equal to dH minus V dP.
Bismillahirrahmanirrahim. My name is Rizwan. So these TDS reactions are developed with an internally reversible process in mind, since the entropy change between two states must be evaluated along a reversible path. However, the results obtained are valid for both reversible and irreversible processes. Since entropy is a property and the change in property between two states is independent of the type of process the system undergoes. Next. So explicitration for differential change in entropy are obtained by solving for ds in equation 7-23 and 7-24. ds equal to du per t um, plus pdv per t, and ds also the differential change in entropy in terms of other properties equal ds equal to dh t dh per t and minus uh, vdp per t.
Okay, now I will continue the presentation for the next subtopic, which is entropy change of solid and liquid. So entropy change during a process is determined by integration to be, as you can see below is the equation for entropy change for liquids and solids. So in the equation there is a C average, which is the average specific heat of the substance over the given temperature interval. So entropy change of a truly incompressible substance, which is liquid and solid, it depends on temperature only, and it does not depend on pressure. The equation can be used to determine the entropy changes of solid and liquid accurately with reason. And liquids can, however, liquids can expand when temperature increase. Therefore, the volume change must be considered in the calculation, as this is a special case. So next, evaluation for isentropic processes of liquids and solids is obtained by the setting by setting the entropy change equal to zero. As you can see below is the isentropic equation, which is equals to zero, and T2 is equals to T1. The temperature of incompressible substance, which is I already stated before, the liquids and solid, will remain constant during an isentropic process. Hence, isentropic process of an incompressible substance is also isothermal.
Okay, so next we will discuss a question for exam for 7.8. Next. So the question stated that liquid methane is commonly used in various cryogenic applications. The critical temperature of methane is 191 Kelvin. Thus, the methane must be maintained below 191 Kelvin to keep in a liquid phase. We need to determine the entropy change of liquid methane as it undergoes a process from 110 Kelvin and 1 megapascal to 120 Kelvin and 5 megapascal. So the first question is we need to determine the entropy change using the tabulated properties, and the second question, determine the entropy change approximate liquid methane as an incompressible substance, and then find the error involved in this question. So we can refer to table 7.1 as the picture at the right shown. At the state 1, pressure is 1 megapascal and the temperature is 110 Kelvin. From table 7.1, we got the entropy is 4.875 and the specific heat is 3.471. For the state 2, the pressure is 5 megapascal and the temperature is 120 Kelvin. Thus, we got the entropy is 5.145 and the specific heat is 3.486. Next. So for the question 1, we need to find the entropy change using the tabulated data. So delta S equal to S2 minus S1. This is the formula. Then we substitute the value. So we got the answer is 0.270 kilojoule over kg times Kelvin. For question B, formula is delta S equal to C average ln T2 over T1. So to find the C average, we use formula CP1 plus CP2 divided by 2. We substitute the value and we got for C average is 3.4785 kilojoule per kg Kelvin. So we substitute to the formula and then we got the entropy change approximating liquid methane is 0.303 kilojoule over kg per kg time Kelvin. So for the error, we use formula delta S actual minus delta S ideal over delta S actual time 100. We substitute the value and we got the percentage error is 10.89%. So that's it from for subtopic 7.7 and 7.8.
Thank you.
Thank
Thank you.
you.
Thank you.